We're going to introduce Chapter 4 by jumping right into a major type of test question found on Test 2. Chapter 4 is about acids and bases. We have to learn that a proton that you learned about before, the thing found in the nucleus of an atom with a plus charge, well, there's a certain element that has only one proton. Which one is that? Hydrogen. And what else does a hydrogen atom have? Only one other thing. It has a proton and an electron. What's the only thing left after you remove the electron? Proton. So you're surprised the symbol for proton is H+? You should not be surprised. That's all there is in a proton. Hydrogen nucleus with a plus charge. I don't like that. That's too big. Won't let me get rid of it either. I tell you, this computer is acting very strangely lately. There we go, 3 times. There you go. Protons. That should be nice. Bronsted acid. It's a shadow. I didn't want a shadow. That's okay. Is a proton donor. Gives up H+, right? Do I have to put down Bronsted base? Talk to me about what a Bronsted base does with a proton. It accepts the proton. Bronsted just means talk to me about protons. From now on, whenever you hear about Bronsted, which is a person's name, useless to us, you just translate in your brain, it's about protons. Okay, conjugate pairs. I'm gonna go to a normal pen here. A conjugate pair, 2 species, different by only H+. What's another way to say H+? Proton. I'm going to keep doing them together, always together until I stop, and then you're just going to hopefully know. Every time he says it, H+, he's talking proton. KEQ and pKeQ are a measure of acidity. KEQ is equal to the concentration of A minus times H, H3O plus, sorry, over HA, where HA is the acid, and A minus is its what? Is its conjugate base. Notice it's different by H+. So this is a generic thing. Once again, there are nice introductory lecture videos on this. I'm just going to assume you know all this stuff. Strong acids and weak acids. Strong acids have Ka greater than 1. That's not very clear. Ka is larger than 1. It's just a way of saying there's more products than reactants in this reaction. And pKa, because it's a log scale, less than 0. pKeq is defined as negative log of KEQ. So as KEQ gets bigger, pKeq gets more negative. So they're in opposite directions, right? Because that negative sign. And they're a log scale, which is powers of 10. It makes the numbers nicer for us. You're going to memorize pKa's for acids. I believe it's on page 120 of the textbook. I was supposed to verify which page this morning, and I forgot. You'll see a video with a blank. And we still have the same blank now. Learn pKa's on page 120. Question mark. could be 122. It's a big table. The whole page is a table. You'll know if you're there. Okay? It's a table. Okay. So you're going to learn them. You're going to use them on every test in this course and the next course. Every single test, no exception. Okay? It never goes away. This is fundamental to the start of this course. This is probably the end of our fundamentals before we get into new things. So, weak acids, Ka is less than 1, pKa greater than 0. When we talk about bases, we talk about strong base, Kb greater than 1, pKb less than 0. Weak bases, Kb less than 1, pKb greater than 0. And you'll see all the derivations of Ka and Kb in the textbook and in videos, lecture videos. You don't have to do derivations in this course. You just have to believe these are true. Okay. So what do we do in this question? This is a major page on this exam. This is just 2/3 of the page. We're supposed to connect the conjugate pairs and fill in the missing piece in the box. There's a step 0 that you should do. It won't ever be written down. Step 0. Cross off spectator ions first. That's metals from groups 1 and 2. Metals from groups I, II. That's periodic table stuff, guys. I see Na here. Now, what is Na's job? You can say it's a spectator. What do spectators do? Well, in sports, they watch. They don't participate, they watch. In a chemical reaction, a spectator doesn't do anything, it watches. It's just there. It's there to balance the charge. What charge was it balancing on the oxygen before you crossed it off? What charge did oxygen have that necessitated the sodium? What's the charge on a sodium ion? +1. So what's the charge on the oxygen? -1. Please put the -1 back. You got rid of its balancing cation. You better show me you know it's charged. Go over here, do the same. And that's all the spectators. Now, the reason you're doing this is so you don't think that things are related because they had sodium attached to them. Couldn't be further from the truth, everybody. What is the relationship between a conjugate acid-base pair? Sorry, say it again. I never gave you this activity? No. Oh, it's not back there? This is number 2. We never gave you this activity. Oh, I found out you can do something on Zoom. You know, some of you are saying, well, my other teacher's been doing this for years. Welcome back. Everybody's got an activity now, and we're going to share our screen. Now, the way I like to start this is connect the pair that is already there. It's catchy, I know. Don't connect the box to whatever it's supposed to be connected to because we don't know what's in the box yet. So the pair that's there is this one. How do I know these are a pair? They're different by only this H+. You put H+ on this O- and guess what you have? This. Also known as bicarbonate. And the question now is, which one of those two in the pair has the extra proton? Because it's the acid. Correct, the first one. And this is where you got to come from your brain and tell me the pKa. And this one gets students because they don't see it as HCO3 negative. They don't. They've learned on the table that HCO3 negative has a pKa of 11, and they don't see that as HCO3 negative. Do you? Do now. There's an H, there's a C, there's 3 O's, and there's a minus charge. That is bicarbonate. pKa on the table is 11. My lab students will tell you that's a bit of a fib. They looked up the pKa, some of them already. But for this course, we're going to the 11 because we like integers. And in lab, we get more accurate things from books and stuff, right? Okay, so we got that. And I'm going to give you another fact here. For a conjugate pair, and you can see this developed in the textbook, pKa for the acid plus pKb for the base is always equal to 14. It's a fact. It's a truth. So if you need to calculate pKb for this conjugate, please organize that equation or reorganize that equation and tell me what numbers to put in here. Oh, tell me what numbers first. Yeah, you gave me the right answer, but then you started with numbers that wouldn't work. 14 minus 11, and somebody said 3 already, which was correct. Yeah. pKb by itself is 14 minus pKa. There you go. So pKb's are easy, aren't they? And that means that these two are pairs, and there's more to it than that, everybody. Every reaction in chapter 4 is an acid reacts with a base to produce a new acid and a new base. That fact tells us that this has to be an acid. How do I know that has to be an acid? Because acids react with bases, and this is a base. So I need a pKa for an alcohol. You're going to learn it eventually, so I'm just telling you right now. 17. This is not a carboxylic acid. Don't give me the pKa for a carboxylic acid. You don't even have ester on your handout because it doesn't have a pKa. Page 120 or 122 doesn't have esters on it, but it has alcohol. So what's the pKb of the conjugate base? 14 minus 17 equals -3. That's a strong base. You know how I know? Strong base. pKb less than 0. This one here was a weak base. How do I know? Right here. It's above 0. So this equilibrium is probably going to go away from the more reactive base towards the less reactive base. Yeah. The more lower the number for any P, pKb or pKa, the lower the number just means more reactive. Stronger, right? Therefore, the higher number means less reactive. What's another way to say less reactive? Okay, weaker, I like your answer. Give me a third way. And talk to me about stability. If you're reactive, you're not stable. If you're unreactive, you are stable. So a less reactive thing is more stable, right? So this is a more stable base here with a higher number, and this is a less stable base with a lower number. Same for the acid. More reactive acid with a lower number, pKa 11. Less reactive acid with a higher number. Equilibrium always points towards the higher number. That's the answer to part C. You point away from the more reactive species towards the more stable species, which is this one. Only look at the pKa's. It can work if you look only at pKb's as well, but it's an extra step for us. Now tell me how to convert this acid into its conjugate base. I have to draw it right there. Remove the H. Careful how you said that. I don't like exactly how you said it. You're on the right track. Don't just call it an H. What is it? Ah, the proton. So what does it mean when you're removing a proton? You're removing an H plus from this O. What's going to be left after you're done? Don't say O. O minus. That's what I want to hear. I just got rid of the NA so I don't ever have to talk about them again. You can put NA there, but please don't. Because students who do not cross off spectators will start connecting this molecule to this molecule because, oh, sorry, I don't like it. No, sorry, I'll go back to what you said. Put the Na there. And they'll say, oh, there's an Na there. It must connect to the other Na right there. That's wrong. Get rid of them. They don't do anything. Don't make them more important than they are. Cross them off. Put their charge that they were balancing on there. Okay. And C points there, and we're going to calculate pKeq. pKeq. This you don't know how to do yet. And here's how. You do pKa left acid minus pKa right acid. That means left side versus right side, people. Every time it's the same. Left acid is 11. Right acid is 17. Negative 6. Therefore, KEQ, how do you undo? Any math whizzes out there? If this is the definition of P is the negative log of KEQ. All you have to do is raise 10 to the power of both sides. You get 10 to the power of pKeq. 10 to the negative log is just negative 1 KEQ. So if you have to go backwards, all I'm trying to say is KEQ is 10 raised to the power of the negative value of pKeq. And somebody gave me the answer already. Equals 10 to the negative 6 equals 10 to the positive 6 means 10 to the power of 6 more products than reactants. You don't have to write that as an answer. That is a way of saying, yes, when I circled the right arrow, the red circle on the right arrow, yeah, it says I'm going to make more products than reactants. The calculation just proves how much more. 10 to the power of 6 more. 1,000,000 times more. This equilibrium is all on the right side for the most part, isn't it? And my apologies for extending this into the next question. Just do a line. Separate the two. There we go. There we go. Ooh, there was a lot there. That was intense. I agree. I don't know what it's doing. I don't even have my toolbar to move, my friend. My computer's telling me to move the toolbar. There we go. And where's your spectator in this next one? That's hydroxide becoming water, right? I saw it. There's the pair that's there. Which one has the extra proton? The one with the extra proton is the acid. pKa for water, you have to learn. 16. pKb for its conjugate base is what? -2. And you guys already knew hydroxide was a strong base. Yeah. Even if you didn't do acid-base chemistry in your previous chemistry, you've probably heard of hydroxide being a base. Yeah. Yeah, negative is negative, and it's strong. And then that means the other pair is, we'll do a purple connection. That pair, right? What do bases react with? Acids. So I'm going to need a pKa for this, and I'm going to give you 3 pKa's, and you tell me which one is the only one that's appropriate. Over here is an H with a pKa of 50. That's an alkane. I'll write it down. Alkane. Over here is pKa equals 45. That's called an alkene. And down here is pKa equals 25, which is the right answer. Why is that the only relevant pKa in this problem? I don't care about the 45. I don't care about the 50. I only care about the 25. Why? Of the 3 numbers, which one is the strongest acid? The 25. What reacts first? Stronger or weaker acid? Stronger acids react first. You must be in this reality, okay? Don't just pick a number because it exists in your molecule. Pick one that's going to react first. And 25 is going to react first. And it's going to give pKeq, right? I'm hard on still. pKb, sorry, 14 minus 25, negative 11. And what do I draw in the box? Didn't change this or this or this or this. Nope, I don't even have that drawn right. Double bind was right there. Oh, I'm not drawing well at all today, am I? And that goes C, triple C. And what do I put at the end of that second C? You took H plus off. Negative. Every time you take H plus off, your charge goes down 1. Okay. All right, why am I circling this arrow this time? Well, the numbers are going to prove it. Calculate pKeq for me. Use the words up here. pKa of the left acid minus pKa of the right acid. 25 minus 16 is what? 9. Keq equals what? 10 to the negative pKeq equals 10 to the negative 9. Yes, equilibrium favors the reactants. 1 over a billion. That's 10 to the 9th in the denominator. 10 to the negative 9. Yeah, equilibrium is largely favoring reactants this time. Okay, so we have that. All right. So here you go. That's it for this video, I think. Did we miss anything? Then P, get the pKq. We're good. Gonna stop it. There we go.